Hi there, this is a very short video, hopefully, on NMR, some aspects of NMR, and Antonio asked for this, so let's get going. So this is NMR, nuclear magnetic resonance, and before we do anything, let's have a look at some of the main concepts of NMR. Okay, these are supposed to be two hydrogen atoms. Okay, there's an electron, and there's an electron, and in the middle there is a proton. And there's a proton. So the NMR I'm talking about here is often known as hydrogen NMR, or more commonly they call it proton NMR. Okay, now protons are little quantum objects and they can have spin. They can spin this way or they can spin this way. Okay, and when they spin one way, we say the spin is plus a half. And when they spin another way, it's minus a half. These are quantum descriptors. You don't have to know about this stuff, but it might help you. These are just descriptions of how they spin. There is a method of finding out how they spin. It's how you grip a pencil in your fist and the angle of your thumb goes and the way your fingers wind around things. So you can actually tell the way things spin, but we're not going to go into that. Anyway, so when we have a little proton spinning, it creates a current, and a current produces a magnetic field. So from this, we can imagine, just looking at the proton is a little bar magnet. Okay, and this proton will be another bar magnet, but will have the opposite direction. So if this one is south and this one is north, this one will be north and this one is south. Okay, so protons have this property called spin. And because they have spin, they can either spin this way, spin up, or this way, spin down. Okay, so if we have lots of protons, let's say lots of hydrogens, there's a hydrogen, and there's a hydrogen, and there's a hydrogen, and there's a hydrogen, the spins will be in all directions, okay? Random, okay? Now, there you go. And so these are random. Randomly orientated. Okay, and if they're all the same, they're all exactly the same, they have exactly the same energy. All of these represent the protons, by the way, this bit. Okay, but as you can imagine, there'll be electrons around them. Okay, but this bit we're looking at, these are the protons. So they have the same energy, and we say they are degenerate. Oh, that's not how you spell degenerates. Let's try and do it properly. Degenerate. So these are degenerate. They're the same energy. So if we were to draw a graph of these, okay, this would be energy. Okay, and we do the protons. They'd all have the same energy, and they'd be all over the place. There'd be angles, like all possible angles, but they would be all the same energy, and they would be degenerate. Okay. Now the interesting thing is, if you put them in a magnetic field, north and south, these protons, well, some protons will align. So these are aligning to the external magnetic field. In other words, this is their south and this is their north. They're doing exactly what you'd think protons would do, little magnets would do in a magnetic field. They would align. So the ones going up and down like this, these are aligned to the external magnetic field. Okay. Now, believe it or not, you will get lots opposed, like this going down. And this one would be south-north, whereas the other one's south-north and south-north. So the ones that point down, in my diagram anyway, these are what we call opposed. Whoops, let me change that. These are opposed to the external magnetic field. Okay. All right, and why do you get these two? Because, well, there's two kind of spin states. There's positive spins and negative spins. All right, so you get aligned and opposed. Okay, when you put them in a magnetic field. Now, when they're in a magnetic field, okay, let me draw the line. Now, when they weren't in a magnetic field, if you remember, they were all degenerate. They were all over the place, weren't they? All of these are degenerate. So this is no magnetic field. But when you do put them in a magnetic field, they split into two. Now, the ones that are opposed, the ones I've drawn going down, are actually at a higher energy than the ones that are aligned. Now, there's a very small energy gap between these two. And it's tiny. It's delta E. And delta E is equal to HF. Okay, where H is Planck's constant. Okay, and F is the frequency of electromagnetic radiation that can be absorbed to go from this state, from the aligned state to the opposed state. So if we give them the right frequency, the protons will flip their states. And all right, and this is called spin flipping. You're flipping it from an aligned state to an opposed state. It absorbs radiation and it goes into the other state. So how much radiation will it absorb? Well, depending on what this gap is. If the gap is small, it will have a small frequency, smaller frequency. And if the gap is bigger, it will have a bigger frequency. So that's what happens. These guys, once you put them in an external magnetic field, they lose degeneracy. That's what we say. Because they lose degeneracy. They lose degeneracy, and there's an energy gap. And when they're in this form, you can zap light waves at them or electromagnetic waves at them, okay, and they will go from one state to the other. So they will absorb electromagnetic radiation. Okay, what part of the spectrum will they absorb in? They'll they'll actually absorb in the radio frequency part of the spectrum, known as RF waves, radio frequency waves. Okay, so first of all, we talked about protons, hydrogen atoms. Okay. Secondly, if you put them in the magnetic field, they either align or they oppose to the magnetic field. And thirdly, if once they are in the field, they have lost degeneracy, and you can zap electromagnetic radiation at them, and they will absorb this radiation. Okay. So that's where we're at the moment. Why hydrogen? Well, because as you probably all know, organic compounds, they all contain hydrogen, don't they? They all contain hydrogen. So it's used to look at organic compounds, basically. All right. I hope that makes sense so far, but I'm going to continue. Please tell me if it doesn't make sense and I'll make a better video. All right. Now, the best thing is to do now is to give an example. And a nice example, I think, is this guy, ethanol. There's ethanol. Now, how many hydrogens does it have? Well, these three are exactly the same. We say they have the same chemical environment. They have the same chemical environment. These two aren't the same as the other three, but they're the same as each other. So these have the same chemical environment. Okay, and this last one, well, there's only one of that. That's got its own particular chemical environment. Now, to be in the same chemical environment, they must be exactly the same. They must be exactly the same. All right. So what does exactly the same mean? Well, let's pick one. Let's pick this one. This one is connected to a carbon, and the carbon is connected to two other hydrogens, and it's also connected to the rest of the molecule. You could say the same about this one or this one. So these three are exactly the same. These two are exactly the same, and this one is exactly the same. But they're not the same as each other. They're the same. Sorry, they're the same as the other CH3 hydrogens. And these acetylene hydrogens, these CH2 hydrogens, are the same as each other, and this OH hydrogen is on its own. So in this molecule, there are three chemical environments. Now, because there's three chemical environments, okay, there will be, each of these will have an associated difference in their aligned and opposed states. So these are the aligned ones. And these are the opposed ones. Because there's 3 environments, there'll be 3 energy gaps. And so we'd expect to see 3 peaks in the NMR. And that's what we do see. The number of chemical environments will give us the number of peaks in our NMR. Okay. All right. Now let's look a bit more closely at this now. Let's call these HC. Let's call these 2 HB. And these 3 HA. Okay, and let's draw the spectrum down here. Let me draw it nicely. Get a ruler out. Hold on. And do the ruler nicely. Yeah. Okay. I want to do it nicely. I rarely do these nicely. So there you go. Nice straight line along there. And let's do a nice one here for this vertical one. All right, and let's make this 90. Nearly there. Oops. Okay, and let's draw the line in there. Whoops, wrong color. All right, there we are. Okay, and this is going to be my my graph, my abundance graph. Now, how much is absorbed? Well, along this axis, we're going to have absorbance. And here, down this side, we're going to have something called chemical shift. Chemical shift is measured in delta, and it's parts per million. And it goes this way: 1, 2, 3, 4, 5, 6, 7, 8, 9. On our course, it goes up to like 12. That's the furthest it goes. Now, there's also going to be a 0. And that's important. I'll tell you why later. So this is the chemical shift. And the chemical shift, let's draw a line in here. This way means increasing frequency. Oops. That's not right. Let's get rid of that. I'm trying to squash it in. So this is increasing frequency down here. All right. So let's have a look at this. Well, this is going to have a peak. The HB is going to have a peak, and the HA is going to have a peak. And it will look something like this. There'll be a small peak at 0, about 1.5. Oh, that's not big enough. There'll be a peak at 0, and then a big peak there, smaller peak, and a smaller peak. You'll get something like this. Now, the HAs are these ones. These are the HBs, and these are the HCs. Now, first of all, they absorb at different frequencies. Why is that? Well, let's have a look at this one first. This hydrogen here. It's going to be a proton surrounded by electrons. Okay, and it's next to an oxygen. Now, oxygen is very electronegative, so it will pull electron density towards it, stripping the proton of shielding, so that the proton here will be deshielded. Okay, if it's deshielded, it experiences more of the external magnetic field, and that means the energy gap will be greater for this proton. Okay, it's in the same external magnetic field, but because you're deshielding it, it experiences more of it. So the energy gap is greater. So the difference here is biggest. So the frequency you need is the biggest. That's why you get a frequency down here. Down this one, the HA protons. Now, these, let's draw this one. The proton here, we're looking at these ones there. The proton here has got its electrons, and it's next to a carbon. And carbon and hydrogen have similar electronegativities. So this one will have its electron field pretty well untouched. So we call this shielded. So that means it can't feel the external magnetic field, and so the energy gap in these protons is smaller. So they will absorb at a smaller frequency. So F is the smallest. And this one in the middle, it's going to be somewhere in the middle. So this is F in the middle. Okay. So that's why you get three different peaks, okay, because of the different chemical environments and whether they are deshielded. If they're deshielded, they'll appear at a bigger number here. And if they're shielded, they'll appear at a smaller number down here. All right, so you get three peaks due to the three chemical environments. Why are they different heights? Well, the area under this one compared to the area under this one compared to the area under this one will show a 3:1 ratio, and purely because this chemical environment has 3 protons, this chemical environment has 2 protons, and this chemical environment only has 1 proton. So they'll absorb different amounts simply because there's more of them. Okay, so this kind of NMR is known as low resolution NMR. Low resolution. Okay, and it basically, the number of peaks gives you the number of chemical environments. Now, that's the basis of this. I'm going to stop there and I'm going to do splitting patterns in another video. But you should understand this first. So I'm going to post this first and see if everyone understands this much. And only then will I go on to the next bit. All right, thank you.